Thanks to Ewan and everyone from P&I for the invitation today. I apologise I could only come at lunchtime, but apparently I missed the best bit this morning. So I've seen Yvonne speak on this topic before. So my group's interested in lipids and lipid self-assembly and making particles from lipids. I'm not going to talk to you at all about, you're not going to see any particles or particle sizing in this talk. You're not going to see anything about RNA or anything like that. But I have to say on both of those topics, we've had projects where we've made mini doxel and got really good tumour penetration using the nanoassembler system, and we've made condensed DNA, plasmid DNA particles that are really good transfection systems without a cationic polymer component or any of those sort of things. So if you want to talk to me about those, we can do that later on. What I'm going to talk to you about is actually trying to use some of these systems for understanding structure inside particles rather than sort of size and manufacture of particles per se. So this work is almost 100% Linda's, so Linda's over there in the corner. So if you want any of the detail, you'll need to ask her, because I'm all about front and very little detail, so for those of you who know me. So we're at Monash in Melbourne in Australia. Tim's been over to visit us on a couple of occasions to help us out with various things. So you're all sitting there and some of you are feeling a little bit tired, and part of that's because your body's working away at lunch and digesting down the lipids to form, to break down the lipids to form fatty acids and monoglycerides. And so part of what we do is we're interested in understanding what happens to the structure of lipids and what self-assembled particles they form. So you all know, I don't know, you must have been asleep all day if you haven't seen a liposome before, but lipids can self-assemble in a range of different geometries, so not just lamellar phase that leads to the formation of liposomes, but you can have some other geometries. So I don't know if you've seen any inverse hexagonal phases today, perhaps, maybe, some of the transfection people. So you can actually make particles from inverse hexagonal phase. We'll see that in a second. And these cubic phases that you might not be familiar with as well, you can also disperse lipids that form those phases. If you disperse those to form particles, then they'll actually retain the internal structure of those sort of more complex geometry systems. So my group in particular is really interested in these sort of materials and sort of controlling the structure of these to do things in drug delivery. So we've got an interest in digestion and what happens during digestion to the structure of lipid particles, and I'll show you some interesting things on that front. And we're also interested in having some of these structured materials where we know if we start with some of these micellar phases, we get really slow drug release from those, but if we use the cubic phase, for example, then we can get quite fast release. So we're actually interested in using that as like an on-off stimulus. So if we can switch between different lipid self-assembled structures and understand how to do that, then we've got the potential to have sort of pulsatile release or on-demand release type systems that have application in a range of different sort of therapeutic settings. And I can talk more about that to you afterwards if you're interested. We haven't really got time here, but we've done all sorts of stimuli with these sorts of materials using heat, pH, salt, redox activity, light, magnetic, and for most of this talk we're talking about enzymatic processes or simple dilution, as we'll see. So we can stimulate transitions between the self-assembled structures just through dilution as well. So that's all nice. So how do we know what we've got? So I'm taking it for granted that we've got these structured sort of internal structures in these lipid particles. So don't take Ben's word for it. We need to be able to measure that. And the way that we go about doing that is with this technique called small angle X-ray scattering. So many of you probably haven't even heard of that before. So bear with me for a second, but I'm going to give you the sort of 101 session on this because it's important for the rest of the talk. But if you have a sample, and in the same way that X-rays interact with ordered, well, many of you will have seen powder diffraction from pharmaceutical APIs, for example. You get a diffraction pattern that has peaks in it, and it's exactly the same situation. If you have a lipid system where there's ordered geometry in that system, it'll interact with the X-rays, generally in a weaker sense than in a powder or bone or some sort of inorganic material. but you still get diffraction, and you can still determine from the diffraction what the internal structure is of the material that you've got in the X-ray beam at any point in time. And so we know what the characteristic sort of scattering patterns look like for cubic phases and what they look like for hexagonal phases, for example. And so we can acquire the scattering pattern, and then we know what the structure is of the material that we've got. So the scattering, all you need to really remember from here on is the scattering pattern's like a fingerprint for the internal structure of the particle. So if we want to know about the internal structure, then we can use this diffraction to understand what's happening. And so that's all well and good, but in the normal sense, if you're applying a stimulus, let's say it's light to... Can I have your glass of water for a second, Ewan, please? Let's say we want to apply stimulus to hexasomes and turn them into cubosomes, then we have to shine light. It's not working particularly well on this thing, but you have to shine apply a stimulus to the material to get it to change. And in a bulk system where you've got a magnetic stirrer and you're pumping through a cell or something, actually getting a uniform stimulus onto the sample is a big problem. And so we're often trapped in this situation where we might actually see a mixture of structures, but we don't really know whether the system truly is a mixture of structures within a particle or whether we've got individual particles with the different structures. And so if we can start to interrogate what's happening to the structure on a sort of scale where we can apply the stimulus completely to the whole volume of material, then we're in a position to better understand and interpret the data that we're getting. So that's where the link into microfluidics comes in this talk. So that's really where Linda's sort of started on this project. So, so how do we then sort of do that with a microfluidics system? So on the previous slide I had that we can have a lab X-ray source where the source of the X-rays is really weak, and to get the sort of diffraction that we see here in a really clean glass capillary, you probably would never get that quality diffraction actually. You'd be acquiring forever and never get the signal to noise. And so that might represent at least an hour or more of acquisition time. So if you want to understand something that's happening on a fast timescale, you've got no chance, because it takes you 1 hour to get a snapshot of what the structure is, and then by the time you go to measure it again, it's already changed. So the point of view of the synchrotron, so a synchrotron's a source of light that is much more intense than what you'll ever get in the lab, and it's much more intense than our sun. So there's high flux of photons, so lots and lots of X-rays. You can tune their energy, you get really good signal to noise, and that allows us to then measure really fast kinetics in these samples, as you'll see, and for weakly scattering samples we can get good diffraction as well. And so what that means is the sort of experiment that might take at least an hour on a lab system, we can do in 10 milliseconds on a synchrotron. So we can now access kinetics that's changing in really fast sort of manner. And so, so I think it might have been Tim was the first person I had this crazy discussion with about, do you reckon we can use the nanoassembler to start looking at some of these processes by putting the nanoassembler in the beam at the synchrotron? And so ultimately the question is, can we see anything through the chip? Because these measurements are still susceptible to background. You need to be able to see your signal above the background from anything else that's in the beam. Most people, if you walked up and said, I want to put this chip in the beam or something, they'd just say, oh, you're crazy. Most scattering scientists would say, you're crazy, just go away and find something better to do with life. And so, of course, this hasn't, the resolution of this has gone a bit funny. So I wanted to put the nanoassembler in the beam. And this was actually inspired by a guy at UCL, Simon Gaisford, who does a lot of thermal characterisation of materials. He went to Mettler and said, I want to drill a hole straight through my DSC so that I can shoot X-rays through the aluminium pan and see if we can do in situ diffraction. And it actually worked. And so that sort of inspired me to say, well, maybe we can just drill a hole in the front of the nanoassembler and then drill a hole in the back and get scattering out of the material that's in the channel, and that'll solve the problem for us. Wasn't one of my better ideas, so the guys quickly convinced me that it wouldn't work. It was too far from where the chip is. The hole would have to be about that round in order to do the sort of thing that we wanted to do. and it wasn't, and we'd have to orient it on a really weird angle and everything else. So that idea lasted about 2 minutes. But then we thought, well, there's nothing to, so what I'm about to show you, Ewan will be horrified. But then it was a case of, okay, well, let's throw the nano-assembler away altogether and use these fantastic chips. And so my second best idea was, I said to Linda, just glue a capillary on the end of the outlet. And so that way we've got our sort of inlets and we've got our long extended outlet thing. And we can then so we would normally use a capillary or a quartz capillary or glass capillary. We'd have our material in a glass capillary for doing these sort of measurements. And so I thought that configuration should work quite well. I have got longer than that, don't I? Yeah. And so, so the idea now was, so what we really wanted to do is, ideally what we wanted to do is follow these processes of transformations between particles using the mixing element and then having some sort of aging of the sample as we go down here. The problem is here we're in the position where we can only, this would in theory work, but we're only sampling from a time point that's, it's a long time point after the initial mixing stage. So we've got we can't see it because we're looking at the back of the chip here. So we have the Y here with the mixing element. And so we're measuring a fair way after the mixing point here. So that wasn't really ever going to be a good idea because we're only measuring what's coming out the end, and then we may as well just capture stuff in a capillary and run it in the normal way. So but we did learn a few lessons about plumbing, etc., in sort of working up some of these ideas. And so this is where we've pretty much ended up now with some of this work, is where we have, so this is at the synchrotron now, so this is our X-ray beam coming in here. And yes, the chip's not in the nano-assembler, so just imagine a nano-assembler around this for a moment. And we need to have nice HPLC fittings to get this to all work nicely. But as you'll see, it's not all bad news. So the X-rays come in here, and we had to drill a hole in the back of the mount, and this is where Tim freaked out. But it still worked okay. It didn't cause any sort of, well, a little bit of leaking maybe, but not too much if you get it right. And then, so the idea then is, because we've got, as you'll see on the next slide, I think. So now we've got our hole in the chip, or in the holder, I should say. X-rays coming in, and we can see the Y, you'll see the Y mixer really clearly in a second. And so we've got around 100 micron resolution with the beam, so we can sample 100 microns resolution with the X-ray beam. So the dimensions are matched about right to see what's going on in the channel, right? So if we mix, we've got a point of mixing. So now in theory we can point the X-rays at any point in the mixing channel and interrogate what the structure is. So we can see in real time what's happening to these structures. So the first thing was, well, actually let's just see if we see something sensible. And so if we put our calibration standard, so silver bohinate's a calibration standard for X-rays, if we just stick that on the back, do the X-rays, the first question is, do the X-rays get through the chip? And they do, so we wouldn't see this sort of even lamellar spacing if that wasn't the case. And then, okay, what if we pre-fill the chip with cubozones? So that remembering that this is a diffraction, or this is a diffraction we should see that I showed on the previous slide, and we see the same diffraction when we shoot with the material actually in the channel, preloaded into the channel. So in theory, we can see the end point. So can we see then, by looking at different points along the chip, can we see what happens at this, during the process of mixing? So this is where we're all getting very excited about this. This thing's crazy idea is going to work, until we started trying to do some dilution type measurements. And so if we take the chip out of the nano-assembler and using our, so we're trying to get the video to run here. There we go. So if we take the chip out and we're using a mixed solvent system and we're trying to do a dilution-induced change from an emulsion to these cubic phase particles, what we actually see is a bit of a pulsing of the flow, and you can get it sort of balanced for a 50-50 mix, but at least more often than not we're really stuck with this pulse flow. We were hoping that by the end of the channel, so we've got here our two solutions coming in and our mixing element, and we're actually shooting with the X-rays up here at the outlet. We're not shooting down here at the initial mixing point, although we can do that. But what we see if we look at the outlet, we were hoping that the mixing through here would be sufficient to sort of, overcome the issues with the pulsing at the Y mixer, but it's not. So what we're seeing here is that at the outlet, we're seeing when the water-rich part goes through, yes, we do see cubosomes, so we're getting a dilution to occur, we're getting the mixing, but when there's a lipid-rich pulse coming through, it's not getting transformation all the way to the cubosomes. We're not getting enough water entrained in that mixing behaviour in order to get full transition to the cubosomes. But at least we're seeing some really interesting mixing here. So what we're doing from a phase behaviour perspective, for those that are used to looking at these sort of phase diagrams, I don't know, is this your one, Johan? Due to ethanol phytontriol water? No? Just propylene glycol phytontriol water. So we're sort of normally, so this is a water-rich end. So what we're trying to do is make cubosomes with a lot of water in them down here, but we're actually oscillating between less water-rich and water-rich environment coming out the end of the tube. So that wasn't quite what we really wanted with this system, although it does show that we can form these systems when you do have a high water content coming through. And so Linda then went away and thought, well, if we're going to think about this in a digestion sense, what we're really going to have is an aqueous phase and an aqueous phase. So perhaps the mismatch in viscosities isn't such an issue when you're in that sort of a regime. And so so if you pre-mix, so if you measure this by fluorescence, and I believe you guys have done a little bit of this, so if you pre-mix at 2 pHs with FTSE in there, then at the sort of equilibrated pH where you preload it with a pre-mixed system, then you see even fluorescence right through the chip, as you might imagine under flow conditions. If you do the mixing on the fly, so we're mixing a high pH and a low pH solution where at complete 50-50 mix we'd expect to see the same sort of fluorescence we're seeing here, then we don't quite get complete mixing. So we can see here that we've got part of the channel that's not completely mixed, at least in this configuration where we've got it outside of the nanoassembler. So whether that's actually the case in practice is, I'm not sure, and I'll be interested to hear you guys sort of take on this. But so that's not quite what so if we're going to now start to think about having an enzyme solution coming in and a lipid solution coming in, that's not really the ideal sort of situation if we're going to try to interrogate a digestion system. So if we want to have, let's say an emulsion come in and a lipase come in and mix, then what we really want is the lipase to have full access to the emulsion in order to digest those lipids and get a transformation to occur. The system that we've sort of been interested in for a little while is, so we're interested in these, I've mentioned that these cubic phase particles, and they're interesting from a number of reasons. They're mucoadhesive, so they have some really interesting applications for that reason, and they're also got potential for controlled release applications, but making them is a real pain. And so normally we'd have to use sonication or some other high energy process in order to make these particles. So a couple of years ago now we came up with this idea, well maybe we can actually have an easy to form emulsion where we have a triglyceride in with a lipid that doesn't get digested. So this lipid here, phytantriol, makes cubic phase particles. So we're same way that phospholipids make liposomes. If you do the same sort of processing with these particles, then you'll get cubosome particles. So I thought, well, at least in the first instance with our digestion studies, let's take this system that we had already shown works in a bulk sort of a mixing vessel and see if we can get that to mix in a microfluidic environment. So we've already seen with on the previous slide with the fluorescence data that we have trouble getting complete mixing in these sort of systems at the sort of flow rates that Linda's interested in for this application. We have to run pretty slow with this. Normally you guys want to run fast to make lots of material in the shortest sort of period of time. We're having to run quite slow with this because what we want to be able to do is to interrogate along the channel the structure, as I've mentioned before. And we couldn't get that with the emulsion lipase system to cut to the chase with this sort of in situ chip, although we're thinking about having a pre-mixing element or making a longer chip or a couple of other approaches that we can maybe talk about. So what I'm going to talk about is doing this still in a microfluidics environment to show that it works, but with potential to go back and look at it in a nanoassembler type or nanoassembler chip. So we had a collaborator in Sydney who uses some of these tea mixing systems to look at some of these sort of mixing processes. And when Linda's run this, when at sort of really slow sort of flow rates that we're interested in, we find that she can actually get the fluorescence of a mixed system to match what we'd expect from the pre-mixed components by the end of these, or at least or almost right through this sort of a microcapillary mixer. So at least in terms of making some progress for a project, she sort of flipped over to that type of a system. So if we do that reaction where we take, what we would normally do with these lipid digestion experiments is we have a really elaborate setup with a pH stat and a burette and an electrode and a peristaltic pump and quartz capillary that we've got to position in the beam. And so the question then is, can we get rid of all of this and just do the mixing on an element that is much simpler? And originally we would have preferred it to have been the Y mixer, but nevertheless, at least if we use this sort of a glass capillary system, can we then interrogate the structure along the capillary, which represents different reaction times? So we've got our enzyme mixed with our emulsion here that's come out of fluorescence measurements, and have the reaction occurring down the capillary, measuring the scattering as we go. So we can interrogate different reaction times by moving the capillary through the beam. And so if we do it with the elaborate mixing vessel and electrodes and everything else, then what we see is we start off with an emulsion and that transforms at a critical point during the reaction to form the cubic phase or cubosome particles. So that's in what we call using pH stat system. And then if we do it in a microfluidics environment, then now we're going from our inverse micellar phase again or emulsion phase to form cubic phase particles. You have to manipulate the flow rates a little, but that's certainly shows that sort of a reaction's possible. So the very last thing I'll show you is what we call a pharmaceutical milkshake idea. So what happens to milk during digestion? So I've shown you this elaborate fight and trial. So the resolution of this has gone horrible, so I'm actually going to skip over that and show that we can form cubosomes, or we can at least see cubosomes on the chip when we digest milk. So when you digest milk, you end up with cubic phase particles, which has turned into a bigger than Ben-Hur story that I'm talking to the Gates Foundation about on Thursday. So I'll finish up there because I'm getting the timer. So this is the group. There wasn't a shadow there when when we took the photo, but Linda is hiding up the back there, and that's what most of our group's interested in. Thanks very much.
So thanks, Ben. Very good talk on how to invalidate the warranty of your nano-assembler instrument.
Not at all. We want to go back, but
so
horses for courses.
We'll be talking to Tim later about this. So it's really interesting, the concept of changing phase to change behaviour. Maybe you could elaborate on potential. I mean, you've obviously indicated you're speaking to the Gates Foundation, so how could this be practically applied?
Yeah, so we already do a lot of work on these stimulated transitions. So you could start from liposomes, for example, and do a transformation to another structured particle with pH, and we've done studies on that to stimulate release from liposomes. And so if you're interested in the sort of subtleties of the phase behaviour, you can, in theory, or you can interrogate that in a microfluidics environment better than you can interrogate it in these sort of bulk flow systems where you may confuse release with like the phase behaviour or phase transition that you see in the scattering might not match to what you're really seeing in release, because you're not applying the stimulus evenly to the whole system. So that's really where it's more about understanding the structure and the transformations in these materials than necessarily having some applied reason for doing this on the chip itself.
Yeah, thank you very much. I really appreciate your talk. Very interesting, very nice work. Just a technical question. What was the wavelength for the X-rays you used for that? Did you go to the hard range to get rid of background scattering, or did you just use the usual 1.4 or 1 nanometer X-rays?
So yeah, a bit lower than that, I should say. So higher energy. So we'd normally use 12 or 15 keV, which it translates to about 0.8 angstroms in the wavelength for these measurements, but we don't have to go to, so we go to 20 keV sometimes for some systems, but we didn't have to in this case. The chip, I mean, you can imagine it's just plastic, so there isn't that much diffraction, but there's a bit of absorption.
Yeah. Okay, thanks.